Welcome to our first Additive Manufacturing webinar, the implementation of HP's polypropylene and TPU printed parts into your end-use assembly. My name is Nika Nami. I'm the marketing coordinator here at Saratech. I will be the host today for this presentation, and we also have two very special presenters. We have Nicole Chowdhury, who is an additive manufacturing lead at Saratech, and we also have Wes Kramer, who is a 3D applications engineer at HP. I'm just going to go over a little bit about Saratech. The Saratech team is a dedicated group of professionals focused on helping customers with product development. We know engineering. Our team has years of experience working with companies of all sizes and industries. Our engineering team uses the software and tools that we sell and support while employing industry best practices and methodologies. And with that, I'm going to go ahead and turn it over to Nicole. Thank you so much for being here with us today.
Well, thank you, Nika, and thank you all for joining us today. I've spent over 15 years in manufacturing and utilizing 3D printing to get products out on the market into your customers' hands as fast as possible. And I wanted to create this webinar series to ease the crippling slowdown caused by COVID and the COVID bottleneck. We are here today to discuss production 3D printing solution multi-jet fusion by HP. This open source system allows plastic manufacturers to develop and provide materials. BASF has done just that for polypropylene and TPU. And we're here to share the diverse applications and even swapping uses that will save valuable development and production time. Let me now turn this over to Wes Kramer, our presenting applications engineer. Thanks, Wes, for joining us.
Hey there, Nicole, and welcome everyone. Thank you so much for taking the time to join us today. I'm very excited to be here and present on some of the exciting materials we have in our portfolio and how those materials are being used in real applications today to save money, to reduce lead times, to make supply chains more robust. And hopefully you will see that we are really making a big difference here in a lot of industries with our materials and applications we are addressing. So let me dive in real quickly to our broader materials portfolio. But as Nicole mentioned, there are a couple materials that we are going to kind of dive in and focus on today in our webinar. So looking at the rigid materials in our 3D printed polymer portfolio, our multi-jet fusion technology, we have a few different types of polyamides. And so a polyamide is a type of nylon. We have a PA11, a PA12, and a PA12 glass beads, which is a glass bead filled nylon 12. Each one of these has kind of their own unique characteristics. They are all very durable, strong materials with great isotropic properties, which is strength in all directions. And they are very commonly used in our technology. They are kind of one of the more traditional types of material sets that are used in powder bed fusion technologies like our own. But today in this rigid polymer category, what I'd really like to focus on and what we're going to be looking at today is our high reusability polypropylene that's been enabled by BASF. And so this is a material that has been developed in partnership with our chemical company partner, BASF. And we are going to dive into this today very shortly here. And so in the elastomeric realm, we have two different types of TPUs and a TPA. All these are very strong, durable elastomeric materials. But today we are going to be focusing on the TPU enabled by BASF. Once again, both of these materials that we're highlighting, polypropylene and BASF TPU, are going to be materials available on our 5200 platform, which is going to be the newer platform in our portfolio of hardware. And so this is why we're going to focus on these today. All right, without further ado, let's take a look at polypropylene enabled by BASF and some of the key characteristics and qualities of the material. What makes it unique and stand out against other materials in 3D printing and manufacturing in general? So polypropylene has been used in a lot of industries for decades now, and it is known for a lot of different things. One of those is chemical resistance. So polypropylene is a very chemically resistant material. It is very largely unchanged dimensionally, mechanically, and by look and feel when exposed to a lot of different very caustic chemicals. Another key highlight of this material and a huge advantage, especially in the automotive industry, and we'll zoom into that a little bit later today, we are able to use the same material in our prototypes as the material the end use product is going to be. Polypropylene, especially in automotive, is very common. And so having these functional prototypes that are 3D printed in the same exact material or very similar material, both functionally and from a weight perspective, as the end use product is going to be absolutely crucial. Polypropylene is what we call weldable, not just to other 3D printed polypropylene parts, but because it is genuine PP, we can actually mold it, or we can actually weld it to injection molded components as well. And that's going to unlock a whole swath of new applications because of that. It's a very fluid tight material with very low moisture absorption. So for a lot of fluid reservoirs or fluid handling applications, it's going to be an excellent choice. It has a high degree of recyclability. This is something that's very important in powder bed fusion technologies. We fuse a lot of the powder in the bed, but most of that powder remains unfused. And so we recycle that unused powder into the next print. And so this reusability ratio of 90% is a very high percentage of material we're able to reclaim and reuse in the next print. And that's going to drive cost of parts down, along with the fact that polypropylene is also the lowest cost material, just pound per pound, in our portfolio. So very low cost parts with this material as well. And then in terms of processability, how the powder is handled and the workflow associated with it is very easy to use, very easy to handle. And so with all this, we're able to address a lot of different applications like tubes, piping, fluid systems, and those are the things we're going to dive into very shortly here. So going over kind of some of the properties of the material, I love this diagram looking at anything from cork as a material, very light, kind of biomaterial there, all the way up to some tungsten alloys. We're looking at the whole spectrum of materials here and how stiff they are versus how strong they are. And so you can see in the middle there, we have our polymer category with things like the PAs, the polyamides, epoxies, polycarbonates. And this is where our polypropylene lies. And so we are kind of in the middle range for mechanical properties within polymers, just polypropylene itself. But then if we take a look deeper at that bubble that says PP, and we look within that bubble, there's different categories of polypropylene. There's a very, very large number of different types of blends and combinations of PP. And so on the stiffer side, we have things like glass-filled or talc-filled polypropylenes. And then on the lower, more flexible side, we have impact-modified PP. And our polypropylene, just to put it in perspective, is kind of smack dab in the middle of those different variations of the material. And so we are balanced. We are somewhere between the stiffer and the more flexible variations of polypropylene. So hopefully that kind of helps shed some light on this material versus other PPs. And then we also have some mechanical properties here listed, kind of comparing to the other rigid polymers in our portfolio, the polyamides. You can see there is a slightly lower tensile strength and tensile modulus, but we have great things like elongation at yield and elongation at break, good impact strength. And then what I really like to highlight here is this low density. And so this is going to be an excellent material for applications where lightweighting is an important function. But this is kind of how it stacks up compared to some of the other 3D printed materials in our portfolio. So let's take a look now at some applications, and I love showing this picture because what it is basically taking this car and dissecting it and laying all the parts out here for everyone to view. And so you can see there's different fabric type components, those seats, there's rubber, tires, there's all these different types of materials. And the question is, how much of this is polypropylene? How much PP is used commonly in a vehicle? So we took a look at some different reports, And today's plastics make up about 50% of a vehicle's volume and about 10% of its weight. If you think about how many metal components in just the engine alone in a car, how heavy all that is, the fact that plastic components that are much, much more lightweight make up 10% is pretty extraordinary. And so a very, very high degree of the components in the bill of materials for an automobile are plastic. And then within that percentage of plastics, about 2/3 of those are made up of 3 different types. And of those 3 different types, polypropylene is the most common at 32% of the 66% of total plastics used in the vehicle. So for this reason, we really, really wanted to develop this sort of unique material in 3D printing to address a lot of functions, especially in automotive, like functional prototypes. And that's exactly what we're going to focus on today for these applications. So let's just take this one example of a fluid reservoir functional prototype. We have some excellent applications and examples here from our service bureau partner, Xtol, that was one of our pilot testers for the material and has had a lot of experience now with polypropylene, with welding, and it has given us some great examples of how this technology is being leveraged. So let's take a look at how this functional prototype might be traditionally fabricated. And so to make a true functional prototype, something that looks, feels, performs like the end use part would, you would have to get a mold developed. Sometimes, with something as complicated as this, you really couldn't machine that. So there's really no option but to injection mold. You could 3D print it, but it probably wouldn't have the same functional properties that the end use part would. Until we came up with a 3D printable polypropylene that very, very closely matches the material performance. So in the traditional workflow, to get that mold, you're looking at something like 7 weeks, especially if you're looking overseas for your mold fabrication. This could be even longer. So just to get that first part to hot plate weld and start doing your validation testing, you're looking at about 7 weeks turnaround time, which in a lot of cases is going to tremendously slow things down. With multi-jet fusion with our polypropylene material, we're talking more about 5 days on that time scale for your turnaround to your first good functional part. And this 5 days is assuming a couple prints, maybe one to test out the original design, kind of measure things, and then one more print to kind of tweak some of the fine critical dimensions just to make sure it is fitting the characteristics needed for the end use application. And so again, you can do your welding the next day, and then within a week, you have your functional prototype ready to go versus weeks and weeks with a traditional workflow. And so this is just one way we are accelerating this development cycle, and we are kind of cutting out some of those liabilities in the supply chain, especially with tool fabrication. So on that vein of fluid reservoirs, why are we looking at this with polypropylene? So why 3D printing in the first place? Really it's, again, shortening that development cycle and getting parts as quick as possible versus waiting on a mold to be fabricated. And then you might find after validation testing that geometry needs to change, and then you have to get a brand new mold made. And so that could be very costly, not just in terms of time, but in terms of money and resources as well. So why multi-jet fusion? Because we are able to print with a very close to analogous material to what their end use product is going to be. And so we use polypropylene because it's going to have the same characteristics as the end use part, and because it's going to be weldable like that end use part needs to be. So you can see this is 2 halves that have been welded together. And so they welded this with a hot plate welding technique, and then they actually did some functional testing on it to see how it performed. And the burst test shown here showed that this survived up to 106 psi on average, which is very close to what the parent material strength would show in that end use injection molded component. So you can see here, I love this burst picture here. It's a great example of how not only did that weld hold up super well, and we actually had failure not on that weld line, but it's showing, up to 106 psi, we are able to have that airtight seal in our material, which is very hard to do in 3D printing, up to the point where we're actually bursting the material. And then very similarly here, we have another example, this time of laser welding, and we're not welding the 3D printed material to the 3D printed material. We're actually welding a sheet stock polypropylene to our 3D printed material. And this is important for a lot of reasons. We're going to take a look at some specific examples soon. But you can see here, this survived up to 150 psi. Again, very close to the parent material strength, and you create that nice hermetic seal. And so it's not just weldable to itself, it's weldable to other polypropylenes because it is genuinely polypropylene, not just some sort of material trying to replicate it. So now we go into, okay, so we can weld this. We've established that it's weldable to injection molded components. How does that come into practice? This photo here looks very simple. It's not the sexiest application, I would say, but what we did here was so crucial. I don't know if any of you witnessing this right now have had this problem happen before, but imagine you go out to get your tool made. It comes back in 7 weeks or so, and in that 7 weeks, the mating component, the mating feature that this component is going to mate with, that changes. And so now your mating features need to change. And so in this case, there needed to be a 5mm offset in order to get this part to function with the end assembly it needed to mate with. And so this was a nightmare for this company, and it happens all the time. Basically you're staring down the barrel of 7 more weeks to get a new tool made, and you're halting production during that time while you're kind of trying to rescue this project. So what they were able to do here is, while they were waiting on that new mold to be made, they were able to 3D print these polypropylene offsets. Very simple geometry here, but they were able to rescue 850 samples. So almost 800 of these components they were able to rescue while they were waiting on that new tool to be fabricated. And so they didn't have to halt production. They could keep moving, and they kind of had this sort of band-aid fix that they were able to implement because of polypropylene and its properties. And this is somewhat similar, a little bit different here, but this company, this large automotive company, was working on a design that we're going to have very limited runs of for a specific market. And so in this market, they needed a specific type of electrical connector. And so instead of having a new tool made for this bigger piece with the new connector type, they were simply able to cut out where the previous connector was, and then 3D print the complicated sort of connector piece, and they were able to weld that to the injection molded component. And so this saved them a lot of money by avoiding having to make a new tool. And because the volumes were somewhat smaller, 3D printing was an excellent fit here, and we were able to step in and supply all those components for that market. So it saved tool time, it saved in time, and it gave us manufacturing flexibility. So a lot of automotive examples there, and that is one of the big places that the material is being used today, but it's not just being used there. We're also seeing it in a lot of different industrial type applications. Again, looking at tubes, piping, fluid systems because of that chemical resistance and that low moisture absorption. We're also seeing it in consumer goods, things like cosmetic brands, because of that chemical resistance. It makes it an excellent material for very cool sort of 3D printed designs like these bottle caps we're seeing here for these perfume bottles. Again, something that you couldn't be able to really traditionally manufacture because of the complexity of the geometry, but with 3D printing, we do have that capability. And then we also see it in medical devices because of the low cost and because of the very lightweight nature of the material. So things like insoles, braces, it can be an excellent material for. Great. So that was it for polypropylene. And now we can go into another very, very interesting set of applications for this material, which is our TPU enabled by BASF. So BASF Ultrasint TPU, some key highlights of the material. It's great for things like flexible lattices. And if you haven't heard of this sort of terminology, lattice, before, and how that's used in 3D printing, we're going to go over some great examples. You're going to see a lot of examples actually, because what latticing does is it enables us to tune the properties of the end part to the function that part requires, all with the same one base material. And so this is going to be a relatively stiff sort of elastomer, but with this latticing, we can do all these different types of tunings based on the application. We're going to look at that. So that's going to make it good for things like flexibility and shock absorption. We get great detail and color uniformity, good reusability and recyclability, just like our polypropylene was 90%. This is going to be 80% reusability ratio in subsequent prints. It's got good UV and hydrolysis resistance. And we can get airtight parts down to 1 millimeter wall thickness, which is a huge challenge in 3D printing, elastomers especially. But just in 3D printing in general, that can be a difficult thing to achieve, but we have that with our TPU. So consumer goods, sports equipment, footwear, wearables, industrial components, we are addressing all these sorts of applications with this material. And after looking at some of the material properties, we'll go into those. So going into the properties, we do have this enabled with a one-pass print mode. That is most materials on our 5200 platform. We'll talk about kind of the throughput improvements because of that. Large range of applications. Again, we'll look at very soon here. But when you're looking at TPUs, one of the first questions that people have is, what's the hardness of the material? And so we use a short A hardness scale. And we are in the kind of upper 80s, low 90s range for shore A hardness. And so this is going to be a pretty hard, kind of tough elastomer. But again, with design techniques, you can soften that up and make it address a lot of different types of needs. And then here we have things like the tensile strength, elongation at break, tensile modulus, rebound resilience, abrasion loss. And we have a few more tests that have been performed from this material as well, if you need to get down to the nitty-gritty details of the material properties. All right, so let's look at our first application here for BASF TPU, which is one that is done by Kupol, which is an excellent design firm. And what you see here is a great example of impact absorption through design. So this is going to be pads for a football helmet. And what I love about this design is their use of this hex pattern on the exterior of the helmet. And, if you think about it, a hex pattern, when you apply a force normal to that hex pattern, you have really, really stiff properties. And so it's almost like the shell on the outside with this hex pattern that's very, very stiff. But on the inside, they're able to kind of to turn that hex on its side. And if you compress a hexagon from its side, it's actually now very malleable and kind of squishy. And so with this very unique sort of complicated design, you have hardness or stiffness on the outside, you have softness on the inside. You're able to tune this and dial this in to have great absorption of impact. And so this is very exciting. This is kind of a concept piece here, but I'm super excited to see how this is going to be implemented in the sports industry in the future to do better than the traditionally manufactured foams that are available today. And then this one is, again, not quite as sexy as an application, but just as important. And it's going to be protecting our parts during manufacturing processes. So this concept of soft tooling, something that is going to protect our parts and fixture them and hold them during the manufacturing process. So this is a great fixture design by Vestas, and they are going to be manufacturers of wind turbine blades. And so with this part, they're able to protect those wind turbine blades, which are very, very high value and very heavy. And this material is going to hold up to repeat use and abuse, and it's going to protect that part at the same time. Another great example of lattice design is this automotive seat which has been produced with the help of Oxer, which is one of our service bureau partners in Europe. And so this is being looked at to integrate into a Porsche design. And what's really interesting here is a couple things. You could have increased breathability from a lattice design like this. So, think about, a hot, sweaty day. These lattice structures allow a lot better airflow and breathability from design. And then you think about different types of people with different types of sizes and proportions. What you can actually do is have them sit on some sensors, some load sensors, and you can actually build a pressure map of what that individual's body looks like sitting in a seat. And then with that pressure map, you can custom tune this lattice in different areas to be as comfortable as possible and distribute that load as evenly as possible for that user. And so again, with lattice design, we're able to do all this custom tuning of properties within the same part using that same one base material. So imagine thickening up the lattice beams in certain sections. That's going to make it stiffer. And then when you make it thinner, it's going to make it a lot more soft. So you can completely customize and tune all around this design for that end user. So super interesting use of a lattice design here. And we have another lattice design being looked at here for an orthotics and prosthetic application. So this is a prosthetic socket, and we have, I believe this is multi-material. Some of it's TPU, the very external part and interior part. And then we have maybe a rigid shell that could be PA12. But in this case, again, you're able to kind of tune the properties of that material to that patient and their pressure map in certain areas to give them the most comfortable outcome possible. Not only that, but if you're thinking about doing this with data and with scans and with pressure maps, you're taking a very artisanal sort of workflow that's super manual and labor intensive and requires a lot of skilled labor. You're taking that process, you're making it digital, and there's a lot of room to accelerate the process and increase throughput by moving to this sort of digital workflow. So very interesting application there, and very excited to see how TPUs are going to be used for things like prosthetic socket liners and others in the field. Looking at sporting goods once again, we have an excellent example of skiing goggles here. And this particular design was basically fabricated to do assembly consolidation. So before, this was made up of a foam component, an exterior component, and there might have been a couple other types of components in here as well. But all with one material, they're able to compress all of those components in the assembly into one part, and they were able to simulate that foam with a lattice design and make it just as soft and conformal as the foam they were using before was. So this is a way to potentially reduce cost. But there's another company, Smith, that made skiing goggles that are a little bit different approach, and what they're looking at is custom fit. So you actually do a face scan, and then you use the data from the face scan to make this conformal fit to the end user. I've tried them on before, and it is night and day when you put those on versus another pair of ski goggles. Very, very cool to see. Then lastly, we have some great footwear applications. And what I love about TPU for footwear is it's really addressing two key things. The first is that you're able to greatly accelerate your development cycle because you're going to be doing all your prototyping in the same material that's going to be used in end use. And so as you iterate, you don't have to kind of then move to your manufacturing material and then readjust based on that. You're able to go kind of straight from that best iteration into your final production design. And so here, this example from Athos is an example of that development cycle being sped up, but it's also a great example of custom fit. I believe this company works off of a scan of your foot to make this custom tailored conformal shoe for each individual user. And so not only are you speeding up your development cycle, but now you're actually giving yourself a competitive advantage against your competition by having these performance boosting attributes that they don't have. Similarly with Hylos, you have these great aesthetic pieces here. These actually have been hydro dipped to simulate the look of wood. but they are being used right now, and there's been tons of reviews, and these shoes are so comfortable, I have been told. I have not tried them on myself, but I have been told that they are extremely comfortable with this unique lattice design that they're able to implement here. So again, not just speeding up development cycles, but actually boosting the performance past the traditionally manufactured footwear in the industry. So in industrial and automation, looking at ways to protect robots, car seats, reduce noise and vibration. There's so many different applications there. In healthcare, with our skin contactability that it has, the biocompatibility, kind of the way to custom tailor based on pressure maps. That's making us great for things like O&P. And then in consumer goods, again, kind of making something specifically engineered for impact resorption, or maybe you want it engineered for rebound and you want as much energy return as possible. We have that ability. We also have the ability to custom tailor for each individual, and we are able to speed up development cycles as well. So those were the two materials we wanted to focus on today. And to wrap things up, I wanted to go over the technology multi-jet fusion that is enabling these awesome applications and materials to be turned into these excellent end-use parts. So let's take a look at the technology very briefly, how it works. We are a powder bed fusion technology, so we are fusing thermoplastic powder together. And how we do this is with our proprietary fusing and detailing agents. And so HP has been a printing company for a very long time now. We are very good at moving fluids to very, very specific, accurate locations with our printhead technology. And we're leveraging that same technology here in 3 dimensions. So instead of printing on paper, we're using our print heads to print on thin layers, about 80 microns of plastic powder, and we're using agents instead of ink here. And so we apply the black fusing agent where we want fusion to occur. We apply detailing agent around the perimeter to prevent that fusion, to keep nice, crisp features. We then apply thermal energy, and we're not just gluing these plastic powder particles together like other types of 3D printing technologies. We're actually fully melting and fusing that plastic to the previous layer. And so we do that over and over again, layer by layer, and then you are left with a fully solid 3-dimensional part over time. And so there's a lot of key advantages here, a lot of great improvements in accuracy and throughput, because we're using a single one-pass system versus using a laser or point-based system to try and trace the outline of each part. We are using powder, so everything is self-supported, no needs for support structures. And then because we are fully fusing layer to layer, we have great isotropic properties, great strength in all directions, and very, very strong end-use parts because of that. And so the workflow, very quickly, what it looks like with this technology, it's a modular system. It was designed that way on purpose. We prepare our 3D files and our build files. We send that to the printer. We have our processing station, which is a very nice way to handle our materials. It's going to mix and load our materials into our build units. And then these build units are going to get wheeled into the printer to start printing. As soon as that print is finished, you can take out that build unit, load in the next build unit, and you can keep that printer going. So that is enabling great utilization of the machine there. You can run the machine around the clock. Once the parts print, they need to be cooled. You have a couple different options here to do it naturally, or a fast cooling option in the processing station. But you use that same processing station to extract the parts, to extract that unused powder, to recycle it and reuse it in subsequent prints. And then we have a bead blasting process at the very end to clean the parts off. And then we also have some optional secondary post processes like painting or dyeing or polishing to improve the aesthetics and other properties of the parts as well. So we have 2 main solutions in our hardware portfolio. We have the 4200, which is the pre-existing solution, and then we have our 5200 series, which is the newer system. And this is going to be a system where we listen to the customer, the install base, and we made improvements on the technology. So this is going to have higher throughput. We're doing a full build in about 11.5 hours here. It's going to have lower cost per part. It's going to have some auxiliary equipment available for it, like an auto unpacker to take kind of the manual steps out of the process and make it more automated. and it's going to have improvements in the repeatability of prints through some better hardware integration as well. So some key attributes that I want to kind of leave on of the technology from multi-jet fusion. We have this area-wide printing process with our print heads that is enabling breakthrough speeds. Our print process doesn't depend on how many parts you're printing next to each other in the build. It only depends on how tall that build is and how many layers you're printing. The layer time is going to be the same independent of how many parts you're printing. So that's going to give us very, very high throughput. We can stack parts on top of each other as well. So we can print a lot of parts very quickly, which is allowing us to address a lot of interesting applications. We are using inkjet technology with our print heads. This is unlocking excellent resolution and accuracy. And because we're using these very strong engineering grade thermoplastics like our polyamides and our polypropylene, right, we are able to get these awesome, strong, durable parts that really do emulate, even injection molded parts. And then material price is also unlocking a lot of applications. This is one of those challenges of additive, but we have very low cost materials just pound per pound by themselves compared to other technologies. And we also have this really high reusability ratio, which allows us to lower that part cost even further. And then last but not least, what's really, I think, allowing us to address so much in the market today, so many different applications and industries, is our breadth of materials we're offering. So we highlighted today our TPU by BASF and our polypropylene by BASF. There's a lot of other great materials in the portfolio as well. And hopefully we get another opportunity another day to kind of go over those and some of those applications as well. So with that, thank you again for taking the time to learn a little bit more about these materials and applications and how we're accelerating our development cycles and being more robust to supply chains. And with that, I will turn it back over to Nika to take us into the Q&A.
Thank you, Wes. Thank you so much for such an informative presentation. I know I learned a lot, and I'm sure everyone else can say that they did as well. Before I get into the questions and answers, I wanted to mention something. We do have these webinars every month, and our next one is going to be on September 7th, and we're going to be going over materials with big reps, so make sure you check that out. And with that, I'm going to go straight into the questions and answers. So our first question for you, Wes, is what do the parts look like coming out of the printer, and is there anything that you can do to improve their aesthetics?
Yes, absolutely. And I might start backing up here in slides so we can take a look at least one example of how we call it post-processing, which is basically what we do to the parts after printing. And so I love this example right here by Hylos. And so these are how parts come out of the printer once bead blasted. You can see they're gray. They're gray because we have that black fusing agent on the inside of the parts, and it's printed on white powder, which is going to, with a little bit of white powder still, semi-fused on the surface, you're going to have a gray part. And so one example of a post-process is hydro dipping, which is a way to basically have ink transfer from the surface of water onto the surface of the part. You can get really great effects from that. There's also post-processing like dyeing and painting, which you can see an example there by Athos. And this is another example of some parts that have been painted. And you also have different things like vapor polishing that can smooth the surface because it is a little bit grainy coming out of the printer. So there's a wide breadth of different post-processing options to improve the aesthetics and the performance of the materials outside of what you just get from the printer.
Can you speak to how much multi-jet fusion can speed up development cycles?
Absolutely, absolutely. So, it depends on the application, and we talked about it a little bit when we talked about functional prototypes. But in that example, functional prototypes, we went from a 7-week turnaround time to get that mold to produce your functional prototype for validation testing. We took that down to under a week. In the case of footwear where you are moving from prototype into production, you don't have to kind of, go in between, again, wait on molds and things. You're going from weeks to days. And so that's really the order of magnitude we're talking about here with speeding up development cycles. The print times, for a full bucket. So if you're printing a build that's completely full, it's under 12 hours in a lot of cases to print that. And then you have to wait maybe, with a fast cool at the quickest another 12 hours. Shorter builds is going to be, something where you come back the next day and you have several iterations already printed and ready to go to evaluate. And so on the scale of days, you're able to iterate through multiple variations of something. And once you have the final version you like, you can start moving into production very, very quickly.
Thank you so much. I'm going to turn this over to Nicole with some final takeaways.
It was so great to learn of these applications and the workflow that your business can implement today to ease your supply chain bottlenecks, shifting the complexity of your system into the advanced technology of multi-jet fusion, really expanding the use of polypropylene and TPU when you need to swap in and get parts fast. I want to, open it up and, offer to continue this conversation offline. Please give me a call and let's definitely work together to see how this can be implemented into your facility. Please follow us and keep up to date on the newest and greatest coming out of HP with the multi-jet fusion. We constantly post details and information as well as coming webinars.
Thanks for checking out our channel. If you like what you saw, make sure to like and subscribe down below so you don't miss out on any new videos. Follow us on LinkedIn, Facebook, and Twitter for the latest engineering news and information. And to see all of our upcoming events, please visit our website at saratech.com/events.